Good afternoon, AP Statistics students. In this lesson, we're going to take a look at one sample t-test, and we're also going to take a look at paired t-tests. These examples correspond to Chapter 9, Section 3 in your textbook. So let's begin by taking a look at this example based on the children's game called Don't Break the Ice. And in case you've never heard of this game before, here you can see a picture of the game. There's this blue square frame with these little white plastic ice cubes, and children take turns tapping on the cubes with hammers to get the cubes to fall through. And you want your opponent to be the one that hits the cube and makes the little red person there fall through the ice. So the cubes need to fit in there pretty perfectly. We don't want them to be too big. It'll make it too tight and hard to fit the cubes out. And we don't want the cubes to be too small because then they'll fall apart and won't even work to fit in the frame. So the plastic cubes are designed to be made 29.5 millimeters wide, but obviously there's going to be a little bit of variability. And to make sure the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. And here we have a sample mean, our sample size, and our sample standard deviation for this particular set of 50 cubes. And so the question is, do these data give convincing evidence that the mean width of cubes produced this hour is not 29.5 millimeters. So we're going to assume the process is in control unless the data suggests otherwise. So let's begin by setting up our null and alternative hypotheses. Our null hypothesis is going to be about a population mean. So this is going to be mu equals 29.5. And the alternative is that mu does not equal 29.5. In other words, the cubes being produced have too large of a width or too small of a width on average. Either way, we're going to have a problem. So we want this to be a two-tailed test. And remember to always state the name of your test. We are doing a one sample t-test. And before we go any further, we should definitely check our conditions. So our conditions are simple random sample, or if we were working with an experiment, random assignment. We have a random sample of 50 cubes, so random sample of 50 cubes, random sample is met. And don't put just SRS or random sample to check. Make sure you note the sample size. It helps to show that you've found where in the prompt that information is located. The 10% condition, it's reasonable to assume, and remember they're sampling the cubes every hour, so it's reasonable to assume there are more than 500 cubes produced in an hour. It's reasonable to assume more than 500 cubes per hour. And then the last condition we need to check is the large counts condition. And we want to compare our sample size to 30. So n is equal to 50, which is greater than or equal to 30. So that condition is met. And this allows us to actually use our t-distribution. We don't need to worry about checking for skewness or outliers in the distribution of our sample, because we know that once we get to around a sample size of 30, normality can be assumed. So we will continue here with this by stating our test statistic formula. So our test statistic formula looks like this. T equals x bar minus mu naught over the standard deviation of our sample divided by the square root of our sample size. So I'm just going to substitute in the numbers that we have. Our sample mean was 29.45. So we have 29.49, excuse me, 29.49 minus 29.5, that's mu naught here. Our standard deviation was 0.09. and our sample size is 50. So let's go to our calculator and enter this in our calculator. So we have 29.49 minus 29.5 in our numerator, and then divided by, and in our denominator we have 0.09 divided by the square root of our sample size, which was 50. And so our test statistic value is negative 0.79 approximately. And what I'm going to do right now is show you how to get an approximate value from the t-table. So from our t-table, and remember you can find your t-table in the appendix of your textbook. So our degrees of freedom is sample size minus 1. So let's go down here and take a look at the row for, well, our sample size was 30. So we're going to take a look at the row for 29 degrees of freedom. And when we look in this row, we can't find the exact test statistic value, but it's somewhere, the negative 7.857 number is somewhere between these two numbers here, between 0.683 and 0.854. So I'm going to scroll up and look at the top of the table here to see what that corresponds to. That corresponds to a tail probability of between 0.25 and 0.2. Now that's actually the area in one tail, and remember this is a two-tail test, so we'll need to double that value. So we're getting an approximate p-value here. Our approximate p-value is between doubling 0.2 and doubling 0.25, so between 0.40 and 0.50, I believe. Let's go back and take a look at that table again. So we had a test statistic value of about 0.79, which corresponded to this row here with 29 degrees of freedom. Oh, actually, I'm sorry, our sample size wasn't 30. Oops, our sample size was 50. So actually we should be looking at a row with 49 degrees of freedom. We don't have that, so let's use this. But once again, it's still going to be between these two values. So the area in one tail is between 0.20 and 0.25. And so we'll double that, and we will get between let's go try this again. Between between 0.40 and 0.50. So it doesn't really matter what the specific p-value is at this point. This is so large, we're going to fail to reject the null. So do we have convincing evidence that the mean width of cubes is not 29.5? We do not have convincing evidence. That the population mean, mu, is not 29.5 millimeters. In other words, even though the average for these 50 cubes was not 29.5 exactly, it was a little bit less than that, it's not that different from the population mean of 29.5. This is just variability that we'd expect to see from sample to sample based on samples of size 50. There was another question here on your notes. It says, do the data provide, at 90% confidence interval for the true mean width, I don't think I have this question here, but a 95% confidence interval for the true mean width of plastic ice cubes produced this hour is 29.46 millimeters to 29.51. So if we had a confidence interval, and this confidence interval was 29.46 to 29.51, would you make the same conclusion with the confidence interval as you did with the significance test? So if you think about it, our null hypothesis was mu equal 29.5, and notice 29.5 is in this interval. So the fact that 29.5 is in this interval means 29.5 is a plausible value for the population mean, which is in agreement with what we concluded for the hypothesis test. By the way, you can do this entire hypothesis test in terms of the test statistic and p-value on your calculator, so let's take a look at how to do that. So we would go to Stat, Tests, and we would choose t-test. And we don't have the original data, we only have the summary statistics, so let's enter the summary statistics. Here this will be 29.5. That's the hypothesized population mean. Our sample mean was 29.49, I believe. Let me just go back and double check that, 29.49. Our sample standard deviation was 0.09. Our sample size was 50. And we need to choose the two-tailed alternative. And I'm going to come down here. I'm actually going to just go to Calculate. And we can see that this test statistic value agrees with what we found earlier. And notice our p-value is between 0.4 and 0.5, which is what we got from our table. So if you have questions about that example, there will be time to ask questions about that in class tomorrow. But we are going to move on to talk about paired t-tests. So if you turn to the next page of your notes, here we have some information about paired t-tests. So comparative studies are more convincing than single sample investigations. So often a subject will be compared to themselves. For example, imagine you're testing sunscreen. It would make more sense to have a person put generic on one arm and the name brand on the other arm, because then we would compare that person to themselves to see how long the sunscreen lasts. That would be more powerful than randomly assigning half of the subjects to the one sunscreen and half the subjects to the other. Because who knows, we might end up with all of the more fair-skinned subjects in the one treatment group, and this way you'd be comparing a person to themselves. So this is an example of what's known as a paired t-test, and we're going to actually be calculating differences, and our null hypothesis is going to be based on the mean difference. So hopefully you've read this section in your book so that you have a better understanding of what paired data are, what paired t procedures are, but we're going to take a look at the following example. So is the express lane faster? So for their second semester project in AP Statistics, these two students decided to investigate which line was faster in the supermarket, express lane or regular lane. And to collect their data, they randomly selected, once again, notice the randomization here, randomly selected 15 times during the week, went to the same store, bought the same item. However, one of them used the express lane and the other used the regular lane. So they're trying to minimize variability related to checkout times related to items or different stores. So they're going to the same store at the same time, randomly selected 15 times. One's going to the express lane, one's going to the regular lane. To decide which lane each of them would use, they flipped a coin, because who knows, maybe Libby's more chatty than Catherine, and that would slow things down. So they've randomly decided who is going to go to which lane. And so they entered their randomly assigned lanes, and they recorded the time it took them to complete the transaction. So is the express lane really faster? And so here we have some data. And at this moment, I'd invite you to pause your calculator and enter your data in list 1 for the express times and list 2 for the regular times. So I've already entered that data in my calculator here in Stat, Edit, List 1 and List 2. And I'm going to go then to the very top of List 3, and I'm going to take List 2 minus List 3, because the order I really subtract these in doesn't matter except for when we define our alternative hypothesis. So we'll talk about that in a minute. But I'm going to go to the very top here and hit second List 2 minus second List 1. So these are the differences. So this is saying that the express lane was the regular lane was 5 seconds slower, right? It took 5 seconds longer. But here, this was ridiculous. The regular lane took 246 seconds longer. But here, the regular lane was actually 46 seconds faster. So let's go back to our screen over here. We did list 3. List 3 was list 2 minus list 1. And so our mean difference is going to be regular minus express. And if the regular, if the express lane was really, really faster in the long run than the express lane, right? If the regular lane is going to take longer, this number would be bigger, this number would be smaller. If this is really the case, and the express lane is faster, then for our alternative hypothesis, we'd expect there to be an overall positive difference in the times here. So I said earlier that it doesn't really matter the order you subtract them in, except when we come down here to defining our alternative hypothesis. If we had subtracted this in the other order and had express minus regular, had done list 1 minus list 2, then mu sub d would have to be less than 0, because then the order of subtraction here would have made the results more negative. If the express lane was slower, this number would have been smaller, this number would have been bigger, our differences would have been negative. So let's check our conditions. So did we have randomness met? Yes, we definitely did. We saw that above. So there was 15 randomly selected times, plus I also had random assignment to who went into which lanes. But we have 15 randomly selected times. 10% condition, obviously this is 15 is a lot less than all the possible days and times they could have gone, so that condition would be met. And we need to also talk about our sample size. So n is equal to 15, and that is not greater than or equal to 30. So the question is reasonable? Is normality a reasonable assumption? So here's what we're going to do. We're going to go back to the calculator, and we're going to go to second stat plot, and we're going to turn plot 1 on, and we're going to turn plot 1 on, and we're going to come down here and make sure we have a normal probability plot selected. So that's selected. And we want to choose list 3 because that's where our differences are located. And we're going to do zoom stat. So if normality is a reasonable assumption, we'd want to look at a dot plot or a histogram or a normal probability plot to make that assessment. And with a normal probability plot, if the points here are approximately linear, then normality is a reasonable assumption. So we're going to go back here and say, however, it is safe to use t-procedures because our normal probability plot was approximately linear. Was approximately linear. Most likely on the AP exam they would give you a graph of the normal probability plot and you would not be entering all this data. That would just be too much time wasted on that. So we're going to actually continue. And you'd want to do a little sketch here of your normal probability plot, so you could go back here and take a look at a little bit of a sketch and just kind of do a little sketch of your normal probability plot to show that you did that. All right, let's actually calculate our test statistic value. We're actually just going to go straight to the calculator for this because I already have the data in my calculator. So this is a paired t-test. Let's write that on here. We're doing a paired t-test. And we always want to report our test statistic and our p-value. So t equals and p equals. And let's go back to the calculator. So stat tests t-test, and we actually are going to use the data that is in list 3 on our calculator. And this will be compared to 0. Go down here to list 3. And this is not a two-tailed test, this is a one-tailed test, where our alternative hypothesis was mu sub d greater than 0, the average difference being greater than 0. I'm going to come down here to calculate. So our test statistic value is about 1.97, and our p-value is about 0.03, we'll say. So 1.97, 0.03, and I believe we're told to use an alpha level of 0.01. So at the alpha level 0.01, this is not quite convincing enough evidence. So at the alpha equals 0.01 level, we fail to reject. And you should always compare your alpha level and p-value. So we fail to reject the null. Oh, that is really messy looking. Let me fix that. We fail to reject the null because 0.03 is not less than 0.01. You always want to link your alpha level and p-value together like this with a comparison statement like less than, greater than. So 0.03 is not less than 0.01. And so what's the conclusion? Do we have convincing evidence that the express lane is faster? Okay, so we do not have convincing evidence that the express lane is faster. All right. And as I scrolled down here, I saw actually I have a normal probability plot that I created in Fathom apparently. That is down here. So there's our normal probability plot in Fathom. So we will have some time to go over any questions you have in class tomorrow. You'll have about a half hour to work on the assignment and get your questions answered. And then we're going to be reviewing for your test, which is on Monday. Have a good afternoon.